Morning friends, welcome to the second lecture of our week number 4 where we are talking about the air standard cycles or so called gas power cycles. Now in the previous lecture we have seen that thermodynamic power producing cycles can broadly be classified into two categories depending on the state of the working medium. The gas power cycles where the working medium always remains in the gaseous phase because the working temperature levels are well above the critical temperature of the substance, whereas the other category can be the vapor power cycles where we have exclusive liquid to vapor or vapor to liquid phase change and operation invariably is limited below the critical temperature of the substance. But in this particular week we are restricting ourselves to the gas power cycles, which are also called the air standard cycles because of the assumptions that we have discussed in the last lecture. Vapor power cycles will be discussed in one of the subsequent module. Now here we have seen that we are primarily focusing on the reciprocating engines or the automobile engines and trying to develop ideal cycles which can somewhat simulate the operation of those reciprocating engines. We have discussed about the different types of reciprocating cycles that or reciprocating engines that are possible, like 2-stroke cycles and 4-stroke cycles. We can have SI engines or CI engines, and accordingly we can have different types of cycles governing the operation of either SI engine or CI engine. We have also discussed about the difference between the ideal cycle and actual cycles. We have seen that while Carnot cycle is the most ideal cycle that we can have because that is a totally reversible cycle, thereby providing the maximum possible efficiency between two temperature limits. Ideal cycles have generally efficiency lower than the Carnot cycle because ideal cycles are internally reversible, but not externally reversible. Like in Carnot cycle, that being totally reversible, we can have heat transfer only in the mode of infinitesimally small temperature difference between the system and the surrounding, which requires either an infinite surface area or infinite amount of time, both of which are practically impossible. Therefore, in ideal cycles, we remove the external reversibility consideration, thereby making the cycle externally reversible and hence allowing heat transfer with finite temperature difference. However, the cycles are internally reversible, that is there is no friction present, and therefore, their efficiencies generally are lower than the Carnot cycle efficiency. However, this ideal cycle is also a kind of assumptions because it neglects the internal irreversibilities and also several complexities that may be present in the actual cycle. Thereby, they provide somewhat upper limit of operation of the actual cycles, which each of the actual engines try to reach. We have also discussed briefly about the Otto cycle, which are the ideal cycle for SI engines. However, because of the time constraint, I was trying to go through very quickly through the mathematical derivation of the efficiency of Otto cycle, for which I made some mistake. Of course, I corrected that, but I am not at all happy. So, to have a proper description of the same thing, I would like to repeat that portion and also some subsequent discussion on the Otto cycle, and then moving on to the next cycle in our course. Now, this is a brief summary of what we have seen. In reciprocating engines, we have seen that in a 4-stroke cycle, generally there are 4 strokes to comprise one particular cycle: the intake stroke, compression stroke, power stroke, and the exhaust stroke. And that is true for both SI engines and CI engines. And we have seen that once we apply the air standard assumptions on them, we generally can identify 4 processes to resemble this 4-stroke. The first process is compression, which actually is a representative of this particular stroke. Second process is heat addition. Heat addition substitutes the combustion process because here we neglect any kind of chemical reaction in the ideal cycle, rather considering the amount of heat produced by combustion to be supplied from some external source by the means of some kind of heat addition. So, heat addition is synonymous to the combustion process that is going on inside the system, something like this one. Then we have the expansion or power stroke, which is representative of this one, and finally we have the heat rejection process, which is you can visualize to be opposite of the heat addition process. And as in air standard cycles, as per our assumption, we are considering it to be a closed system, thereby completely eliminating any inlet and exhaust processes. So, the heat reaction process actually allows it to be considered as a closed system and get the system at the end of expansion stroke to back to the initial point of the compression stroke. So, these are the 4 processes that primarily constitute any air standard cycle. but different air standard cycles can be conceptualized depending upon the individual nature of all these 4 processes. Firstly, heat addition and heat rejection. That is where primarily the difference lies. But before that, we have the compression and expansion processes. Now, compression and expansion processes, as we are assuming the systems to be internally reversible, so they are always frictionless. Along with that, if we assume the systems, or along with that, if we assume these 2 processes to be reversible as well, then that is the best possible performance that we can get. Like, if we, what we are saying is that as the cycles are already, all these processes are already internally reversible, plus if we assume them to be adiabatic, then we get this compression process to be isentropic. And we know that when a process is isentropic or reversible adiabatic, then we can compression is a process which requires work input from outside, then it is possible to have the smallest possible work input. Similarly, if we have the expansion process to also be isentropic, then it is possible to have maximum possible work output from this cycle, and that is why this compression and expansion processes are always assumed to be isentropic. But heat addition and heat reaction can vary. Like when this heat addition and heat reaction processes are, if we are assuming the heat addition process to be isothermal, or I should say reversible isothermal, and similarly the heat reaction as well to be reversible isothermal, then what we get? This isentropic compression and expansion, reversible isothermal heat addition and heat reaction, that is of course our most ideal cycle, which is the Carnot cycle, where heat addition and heat reaction processes are also externally reversible, as we are considering reversible isothermal heat transfer with infinitesimally small temperature difference between system and surrounding. And in case of ideal cycles, we can't have isothermal heat addition and heat reaction, we need to have something else. So, when heat addition and heat reaction both are considered to be isochoric, means happening at constant volume, then the cycle that we get, that cycle is called the Otto cycle. In Otto cycle, both heat addition and heat reaction are isochoric or happening at constant volume. This is the ideal cycle for SI engine. Whereas, when the heat addition process is assumed to be isobaric, that is happening at constant pressure, whereas heat reaction remains isochoric, then the cycle that we get, that cycle we call the diesel cycle. This is the ideal cycle for the CI engines. Similarly, it is also possible to conceptualize another cycle where heat addition and heat rejection both are isobaric. That particular cycle is another air standard cycle known as the Breton cycle or Joule cycle. But this is generally not used in reciprocating engines, that rather it is used more in gas turbine kind of rotary devices. This one we shall be discussing in the corresponding week. But here we are primarily focusing on the Otto and diesel cycle. So, in case of Otto cycle, we have the heat addition process to be isochoric, whereas in case of diesel cycle, we have the heat addition process to be isobaric. In both cases, heat reaction is isobaric in nature. So, now we want to discuss about the Otto cycle first, and then moving on to the diesel cycle, and then a combination of these two in the form of a dual combustion cycle. But before that, I would like to quickly mention about the one of the assumptions under the air standard assumptions, which is we are assuming the working medium to be air, which is assumed to be an ideal gas. That is a very good assumption, as that simplifies our analysis quite a bit. As we are assuming air to be an ideal gas, so we can always represent it by this equation of state P v equal to R T, where V is the specific volume, P is the pressure, T is the absolute temperature, and R is the gas constant. Typical value for R is 0.287 kilojoule per kg Kelvin. So, this is a constant, this is always known. And another assumption that we have considered, that is the specific heats to be constant. We have assumed the specific heat Cp and Cv to be constant. Now, Cpu upon Cv, this ratio is given by K, which I have already used in Otto cycle. So, as we already know the value of R, which is a constant for air, then truly speaking, while solving any numerical problem, we need to know just one among these three, Cp, Cv and K, because what is the relation of Cp with R? We know that Cp minus Cv is equal to R, and now we have Cp upon Cv equal to K. Therefore, if we know any one of these three, that is K, Cp and Cv, if we know just any one among the three plus R, which is already there, then we can calculate the other two as well. So, though in several textbooks you will may find some given value of Cp, Cv etc., but we shall be following this methodology where we are going to take R as a constant, and we are going to get one of the specify one of them, one of the three, either K or Cp or Cv, and remaining two needs to be calculated from there for any given situations. Now, we move to the Otto cycle. These slides I have shown in the previous lecture itself. Nicolas Otto is a Frenchman who was the first to conceptually develop the cycle. The one that is shown here, that is what goes in practice, but this is the corresponding air standard version of this, where we have the isentropic compression process as 1 to 2. So, we have 1 to 2 as isentropic compression, then we have 2 to 3 as isochoric heat addition, then we have 3 to 4. What is your 3 to 4? 3 to 4 is again another isentropic process, but during which the volume is increasing, pressure is decreasing. So, it is an isentropic expansion process, and 4 to 1 is isochoric. Just we have discussed in the previous slide, it is an isochoric heat rejection process during which the volume remains constant. So, here the smallest possible volume the system can have is this V2, which is equal to V3, which corresponds to the top dead center. Here this volume, that is V2, which is equal to V3, is nothing but the clearance volume, because the piston is at the top dead center corresponding to this location. Whereas V1 and V4, they are also equal, because 4 to 1 is an isochoric process, and this corresponds to the bottom dead center, which is having the total volume. And as per our definition, Vt upon Vc is given by the compression ratio. So, this compression ratio here can be represented as V1 upon V2 as well, or we can write in terms of V3 and V4 as well. So, this is the corresponding PV diagram and TS diagram. Look at this, 1 to 2 and 3 to 4 are isentropic processes. So, they are given by vertical lines, no heat transfer along them, only changes in the value of temperature, but entropy remains constant. Whereas, during 2 to 3, temperature and entropy both are increasing. As entropy is increasing, so it signifies that it is a heat addition process, because you have to remember that it is an internally reversible cycle. Therefore, during 2 to 3, there is no entropy generation, and so entropy of the system can only increase because of heat addition or entropy transfer with heat addition. Similarly, 4 to 1 entropy is decreasing, which signifies this is a heat rejection process, because entropy can decrease during a reversible process only when heat is being rejected by the system. So, we have to perform the mathematical analysis of this one quickly, something that we have done in the previous lecture, but I would like to repeat that one, because the mistake that I did there, I do not want to do it once again this. So, here we know that just what we have done earlier, the amount of heat transfer can be used to get the expression for the efficiency, sometimes called the thermal efficiency or first law efficiency, which is net work output divided by heat input given. Here we are using small w and small q to denote, it is per unit mass, and as using the first law expression, we can write this as q out upon q in. So, we have to get q out and q in. Now, during process 2 to 3, we have heat addition, during 4 to 1 we have heat reaction, whereas during 1 to 2 and 3 to 4 there are no heat transfer. So, we have to analyze each of the processes individually to get this q out and q in. As there is no heat transfer involved with 2 of the processes, let us skip them for the moment. We are just going to analyze 2 to 3 first. So, for 2 to 3, if we write the first law of thermodynamics, then we can have Q223 minus W223 is equal to rate of change of energy of the system, that is E3 minus E2, and as we are generally assuming this one to be a stationary system. So, this one can be written as U3 minus U2, as the changes in kinetic and potential energies of the system is negligible. Now, Q223, during this process heat is being added. So, Q223 is integral Q in. W223 can be considered as integral P dV during this process. Now, volume remains constant. So, that becomes equal to 0. So, we have this 0 equal to U3 minus U2, which gives us Q in is equal to U3 minus U2, and as we are dealing with an ideal gas, during where the change in space internal energy can directly be related to the change in temperature in terms of the specific heat, which is again assumed to be constant. So, we can write this one to be Cv into T3 minus T2. You can refer to our secondary discussion where we developed the expression for du. If you put the ideal gas equation, I think we did one exercise also. If you put the ideal gas equation of state there, you will find that du will be equal to Cv dt. So, we get Q in. Instead of writing this way, we could have converted everything in terms of rate equation as well. That is our wish. And now we have to analyze 4 to 1. If we want to write in rate equation, we have to put a dot on top of everything. There is Q dot and W dot like this. For 4 to 1, what we can write is the same way, Q 4 to 1 minus W 4 to 1 is equal to U1 minus E4, that is similarly U1 minus U4. Now, during this process heat is being rejected. So, Q 4 to 1 as per our convention is minus Q out, because we are taking heat rejected by the system to be negative, minus W. Now, W 4 to 1 refers to integral 4 to 1 P dV. Again it is an isochoric process. So, this is equal to 0 again. So, minus 0 is equal to U1 minus U4, which gives us Q out to be equal to U4 minus U1, that is equal to Cv into T4 minus T1. Now, we go back to our expression for efficiency, which is 1 minus Q out upon Q in, that is 1 minus, we use the expressions that is derived here. Q out is Cv into T4 minus T1, Cv into T4 minus T1 by Cv into what was our Q in, Cv into T3 minus T2. So, Cv cancels out, and by taking T1 common from the numerator and T2 from the denominator, we can write this one as T1 into T4 upon T1 minus 1 by T2 into T3 upon T2 minus 1. Now, to get the values for this temperature, we have to look to the process itself, other two processes rather, these two isentropic processes. Now, during 1 to 2, it is being an isentropic process, the process equation can often be represented as Pv to the power k equal to constant. So, where k is the ratio of specific heat and P is the pressure, and from ideal gas equation of state we know that Pv equal to RT. If we impose it here, we can write this to be Tv into k to the power T into V to the power k minus 1 to be equal to another constant. So, if we use this now for the process 1 to 2, I would like to request you to check this from Pv to the power k, how we are getting Tv to the power k minus 1 by using Pv equal to RT. R becomes a part of this constant now. We just have to replace P. So, if we put this now, Tv to the power k minus 1 equal to constant for process 1 to 2, we can write T1 V1 to the power k minus 1 is equal to T2 into V2 to the power k minus 1, which gives us T1 upon T2 to be equal to V2 upon V1 to the power k minus 1, and as we have seen from the previous slide, V1 upon V2 is equal to R. So, that gives us 1 by R to the power k minus 1. Now, check out process 324. 324 is another isentropic process. So, during this particular process, we have T3 V3 to the power k minus 1 is equal to T4 V4 to the power k minus 1, which gives us T4 upon T3 to be equal to V3 upon V4 to the power k minus 1, and considering the two isentropic processes, we know that V3 is equal to V2 and V4 is equal to V1 to the power k minus 1, and from here we know that V1 upon V2 is R. So, it is by R to the power k minus 1. So, what we have then? We can write T1 upon T2 is equal to T4 upon T3, or if we reorient this, we can write T4 upon T1 is equal to T3 upon T2. So, if we take it back to the expression for eta, then we are left with 1 minus T1 upon T2, and T1 upon T2 is nothing but this. So, we have 1 minus 1 by R to the power k minus 1. So, the thermal efficiency for the Otto cycle is a sole function of the compression ratio and the K for the substance. Maybe we can write this way. So, it depends on only two things, one is the compression ratio and another is the K for the substance. For a given substance, K can be taken as a constant, then it depends only on the compression ratio. And like I have mentioned in the previous lecture, compression ratio is the first most important parameter that can govern the performance of a system. So, that is what you have here. The efficiency is depending only on the compression ratio for a given substance. So, this way you can calculate the efficiency, and if your objective is to get some other parameter, like if you want to calculate the work output, how you can get it? The net work output W net can easily be obtained as the eta thermal into Q in from the efficiency expression this. So, this way you can calculate the work output. If your objective is to calculate the individual heat transfer values, then actually in the next lecture we shall be solving some numerical problems, but one important suggestion there I can give here, that do not try to remember the expressions for these efficiencies. For Otto cycle it is very simple, so probably you can remember this, but the subsequent two that we shall be doing today, it will be very difficult to remember those expressions, and there is every chance of making some mistake if you are trying to solve some numerical problem by remembering those equations. So, always try to come from the first principle, that is just try to calculate the heat transfers, say how much will be your Q in, the amount of heat transfer. In this case Q in corresponds, like we have derived in the previous slide, Q in will be equal to Cv into T3 minus T2. Similarly, your Q out will be equal to Cv into T4 minus T1. So, if you know this know the temperatures involved in the cycle, then you can easily calculate Q in and Q out. Now, your cyclic integral of del Q here is Q in minus Q out, and as per the first law of cycle, that has to be equal to W net, and once you know Q in and Q out, again from here you can easily calculate the efficiency without trying to remember this. So, this way several things can be calculated from the cycle, just from the knowledge of this Q in and Q out. Now, if we plot the expression for eta thermal with R, then we can get a curve like this. You can see with increasing compression ratio, efficiency keeps on increasing sharply, or at least for lower values of compression ratio, the slope is very steep, like in this portion. However, it settles down quite a bit in here. So, as we go to higher compression ratio, the incremental increase in this thermal efficiency is lower, but you never reach a point of inflection, it keeps on increasing continuously. Similarly, the effect of K is something like this. Smaller the value of K, higher will be the efficiency for a given compression ratio. So, if we have two identical SI engines, one working on say helium, which is a monoatomic gas, and other working on say air, which can be visualized to be a diatomic gas, then for the helium one is going to give you higher efficiency because for the same compression ratio, because it has a lower value of K. This corresponds to roughly monoatomic gases, this is approximately for diatomic gases, this is approximately for triatomic gases. So, K keeps on, as K keeps on increasing, the thermal efficiency keeps on reducing. In practical engines, we generally have heavier molecules like carbon dioxide or carbon monoxide or sometimes methane, etc., which have much lower value of K, K in the range of 1.2 or even lower. So, their efficiency will definitely be much lower compared to these ideal cycles. Now, you can see here I have given a range of typical compression ratios for gasoline engine. If we can get higher efficiency by working at a higher compression ratio, then why you do not need to, why we are not going for such very high compression ratio, why you are restricting it to such a narrow band, something like 7 to 10 as shown here. Practical SI engines hardly have compression ratio greater than 10 or 12. That is because of the temperature consideration. You can see from the previous slides that as the temperature, sorry, as the compression ratio increases, the temperature also increases, because we have just seen that T2 is equal to T1 into R to the power K minus 1. So, as R increases, T2 keeps on increasing. So, higher the compression ratio, temperature of the gas or air at the end of compression, that also keeps on increasing. Now, in ideal case your working medium is air, so there is no issue, but in actual cycle we have some hydrocarbon fuel, and every hydrocarbon fuel has a auto ignition or self ignition temperature. Now, if during the compression process we set the compression ratio such that the T2 becomes higher than the self ignition temperature, then before the compression process finishes, the mixture or your fuel will start to self ignite, which is highly undesirable process. So, and that is why we want to restrict our compression ratio such that this auto ignition can be avoided. We set compression ratio such that T2 should always be greater than the auto ignition temperature for the fuel that you are dealing with, so that the auto ignition can be avoided. If the system or if the fuel auto ignites, then that leads to something known as the knocking, engine knocking. There is one number called octane number. I can't discuss this here because that is a topic that is beyond our scope, but octane number generally is a criteria that is related to this auto ignition temperature, and that identifies whether the fuel is going to auto ignite or not for a given compression ratio range for this. So, but in a nutshell, we have to keep the auto ignition, keeping the auto ignition temperature in mind, we have to keep the compression ratio limited. Several attempts has been done to improve this octane number and thereby to increase the auto ignition temperature. Like since 1920s, people started adding lead to the gasoline fuels, which is a quite inexpensive option of increasing the octane number. Addition of lead has shown to increase this auto ignition temperature quite markedly. However, when we came to 1970s, it has been observed that because of the presence of lead during the combustion process, lead participates in the chemical reaction and produces several very harmful gases, which are harmful to our health and of course leads to severe environmental pollutions. And that is why since 1975 gradually the lead has been phased out from the gasoline because of the international protocol. In fact, after whatever automobile vehicles that were fabricated after 1975, they are all suitable for unleaded gasoline, and so we are back to lower compression ratios. Nowadays people use several kind of gasoline blends, etc., which has been able to increase the auto ignition temperature a bit and thereby causing or affecting some small amount of change in the effective range of compression ratios, but still some way to go. This is a very active area of research and quite open area of research, where we are looking to increase the auto ignition temperature of the fuel by making some blend or by adding something to the raw gasoline, and so that we can cause some increase in the compression ratio. Even one level increase in the compression ratio can cause some 2-3% change in this auto cycle efficiency, which actually can lead to huge amount of fuel saving. That is why it is extremely important. Now, we move to the second one, which is the ideal cycle, diesel cycle, called the ideal cycle for CI engines, where in fact we can go beyond this auto ignition temperature limit and go to much higher compression ratios. As the name suggests, it is the engine which uses diesel group of fuels as the working fuel. Rudolf Diesel, the picture shown here, he was the German scientist who was the first inventor of the CI engine concept. The most important difference between SI engine and CI engine are in this ignition process. In case of SI engine, we have a fuel air mixture which is generally prepared inside a carburetor that is supplied during the intake process. So, during the intake process, a fresh fuel air mixture is supplied to the cylinder. Now, during the compression process, the fuel air mixture is compressed to a high pressure and temperature limit or temperature level. However, we have to limit the temperature below the auto ignition temperature, then we produce the spark, so that the combustion is initiated. In case of diesel engines, during the intake process we supply only air, no fuel during the intake process. So, it is only air which is supplied, quite similar to the ideal one. It is air which is supplied during the intake process, it is air which goes through the compression process. As there is no fuel inside, so we can go to any temperature limit inside during the compression process. There is no auto ignition temperature limit, so we can easily heat air to very high temperature, or I should say we can compress air to very high pressure levels, so that the temperature can be well above the temperature of the corresponding auto ignition temperature of the fuel. And now, at the end of this compression process, there is a fuel injector. In case of SI engine, we had this spark plug. Here we have the fuel injector. Here liquid fuel, that is diesel, which is sprayed inside the combustion chamber at the end of the compression process. As the liquid fuel comes inside, the fuel droplets are immediately exposed to an environment which is maintained at a temperature well above its self ignition temperature. So, they auto ignites or self ignites. Therefore, self ignition is actually desirable in case of diesel engines. So, in case of gasoline engines, the ignition is initiated by a spark plug. So, we have spark initiated combustion or spark ignition, whereas we have self ignition here in case of diesel engine. In order to have this self ignition only, we supply only air during the intake process and compress that air to a very high temperature, and then the fuel is sprayed inside. That is a major difference in CI engines. So, it is only air which is supplied during the intake process, air is also compressed because there is no fuel inside. So, we do not have to be bothered about the auto ignition temperature limit, we can compress air to very high pressure levels, and therefore, we can go to much higher compression ratios in case of CI engines. Fuel is injected at the end of compression process. As the fuel comes in, invariably the temperature is well above its auto ignition temperature, and therefore, the fuel auto ignites. Then spark plug and carburetors are not required, because spark, we do not need to produce any spark. So, spark plug is not required and carburetor is required to prepare a fuel air mixture. Now, as we are not preparing fuel air mixture, air is supplied at the beginning of inlet process and fuel is sprayed after the compression process. So, carburetor is also not required, but of course, we have a fuel injector and we generally also need to have a fuel pump, because the pressure of this fuel also needs to be higher than the pressure of air for it to be sprayed inside this. So, we need to have a fuel pump and a fuel injector or spray gun, which are in fact much costlier and heavier compared to the spark plugs and carburetors, and a higher compression ratio, as I have mentioned. But one drawback here is there is possibility of incomplete combustion, because in case of SI engine, the fuel and air are uniformly mixed in the carburetor before supplying to the cylinder. So, every fuel molecules generally has sufficient number of air molecules around it, but here in diesel engine, as the fuel is being sprayed inside, so it is very much possible that some of the fuel droplets or fuel molecules may get sufficient amount of oxygen in the neighborhood and some of the droplets may not get any. So, it is possible some amount of fuel may remain unburned, leading to incomplete combustion, loss of fuel and subsequent pollution problems, which is not that much significant for SI engines. So, spark plug and carburetors are not there. Instead of that, we have fuel pump and fuel injector, which are costlier and heavier compared to spark plugs and carburetors. So, here the combustion, as I mentioned earlier, here the heat addition in ideal cycle is visualized in the mode of constant pressure, because in case of SI engine, as soon as we are initiating the spark, the combustion happens, and it happens almost instantaneously before the piston starts to move again. That is why we assume it to be a constant volume combustion. However, in case of CI engines, as we are spraying the fuel, that requires a substantial amount of time to supply a fixed mass of fuel, and by that time the piston definitely keeps on moving. So, we generally try to spray the fuel such that the pressure inside remains constant, thereby achieving this combustion process at constant pressure. However, there is change in volume, like this is your bottom dead center location, and this is the top dead center location. If I draw like this, this is your BDC and this is your top dead center, and this combustion process actually happens over this particular volume. So, there is a good amount of change in the volume of this, and the total volume available for the expansion process is only this much, whereas the entire change from clearance volume to total volume is available for expansion in SI engine. In CI engine, that is lesser. We of course want to reduce this one as smaller to a smaller level, but that depends upon how much mass of fuel you have to inject and also the design of the injector. This is the corresponding TS diagram. One important consideration that we must do here, that is the slope of this constant pressure line. Now, from our earlier discussion, we know that the slope of on a TS diagram, the slope of a constant volume line is generally given by CV, whereas the slope of a constant pressure line is given as 1 upon Cp. Now, we know that Cp is greater than Cv. So, 1 upon Cp is less than Cv, therefore, the slope of a constant pressure line is less than the slope of a constant volume line. So, from point 2 we have to draw a constant pressure line, which is shown here for this. And here to characterize, along with the compression ratio, you have to define another parameter. So, the compression ratio here remains the same, that is volume before compression by volume after compression, V1 upon V2. Here we define a new parameter called the cutoff ratio. Cutoff ratio given by RC, which is given by volume after combustion, that is V3 by volume before combustion, V3 upon V2, volume at the end of combustion to volume at the beginning of combustion. This is a new parameter that is required for diesel engines. So, if we analyze it again, so we shall be trying to do it quickly. So, here the thermal efficiency is again 1 minus Q out by Q in for process 2 to 3. For process 2 to 3, Q 2 to 3 minus W 2 to 3 is equal to U 3 minus U 2 as earlier. Now, Q 2 to 3 is Q in, but W 2 to 3 is not 0 in this case, because it is not a constant volume process. Now, W 2 to 3 is equal to integral 2 to 3 P dV. Now, pressure remains constant during this process, is not it? So, we can write this to be equal to P into V 3 minus V 2. So, Q in will be U 3 minus U 2 plus P into V 3 minus V 2, that is we can write this to be equal to U 3 plus P 3 V 3 minus U 2 plus P 2 V 2, as we have P 2 equal to P 3. What is U plus P V? That is enthalpy. So, it is H 3 minus H 2, and for an ideal gas we know this is equal to C P into T 3 minus T 2. Similarly, for process 4 to 1, we can write the same way whatever we have done earlier. Q 1 to 4 minus W 1 to 4 is equal to U 1 minus U 4 Now, Q124 is minus Q out, it is a constant volume process. So, it is equal to 0 is equal to U1 minus U4. So, Q out is equal to U4 minus U1 is equal to Cv into T4 minus T1. If we want to analyze this now, then eta is equal to 1 minus, let us try to do it here itself. Eta is equal to then 1 minus what is our Q out, that is equal to Cv into T4 minus T1, it is Cp into T3 minus T2, that is Cp minus Cp upon Cv is k. So, we can write it to be 1 upon k into the same way. If we take T1 common from here, okay, there is no need of doing this for the moment now. Let us just write it as the ratio of temperatures, that is T4 minus T1 by T3 minus T2. Now, we have to evaluate each of these temperatures. So, let us try to analyze each of the process one upon one. Now, 1 to 2 is a constant, or sorry, it is an isentropic process. So, for an isentropic process, we have already seen that we can write T2 equal to T1 into R to the power k minus 1. 2 to 3 is a constant pressure process. So, for a constant pressure process, we can write using the ideal gas equation of state, we can write P2 V2 upon T2 is equal to P3 V3 upon T3, that is T3 upon T2. P2 and P3 are equal to each other because it is a constant pressure process. So, T3 upon T2 is equal to V3 upon V2, which is equal to RC, which we have just defined. So, T3 is equal to T2 into RC, that is T1 into RC into R to the power k minus 1, that is for process 2 to 3. Similarly, for process 3 to 4, look at the diagram. 3 to 4 is an isentropic process. So, for an isentropic process, just like we have written earlier, T3 V3 to the power k minus 1 is equal to T4 V4 to the power k minus 1, that is T4 upon T3 is equal to V3 upon V4 to the power k minus 1. And what is your V3? V3 is RC into V2, and V4, what is your V4? Look at this diagram, V4 and V1, 4 to 1 is a constant volume process. So, V4 and V1 are equal. So, V4 is equal to V1 to the power k minus 1, that is equal to RC upon R to the power k minus 1. So, we have T4 equal to T3 into RC upon R to the power k minus 1, from where you can actually put back the T3 expression in terms of T1. Now, if you combine all of them, then I am directly writing the expression for the efficiency for diesel cycle. You just have to take these 3 expressions for T2, T3 and T4 and put it here, and if you do it, you are going to get the thermal efficiency for an ideal diesel engine to be 1 minus 1 by R to the power k minus 1 into RC to the power k minus 1 by k into RC minus 1. This is the expression for the ideal diesel cycle. If we plot it in terms of compression ratio, again you will be seeing that for a given value of RC, R keeps on increasing. Typical compression ratio for diesel engines is much larger. You can see the range is 12 to 23, 24 in that range, which is well above the same for SI engines. CI engines are used in heavy vehicles where you need larger powers, like in case of buses, trucks, ships, etc., where you go for CI engines, whereas SI engines are commonly used in two-wheelers, smaller passenger cars, etc. Electric trains can also be an example of CI engines. Whereas SI engines we generally are restricted to low power applications because the compression ratio is lower. One important or interesting thing that you can see, if we put RC equal to 1, of course this expression will lead to a 0 by 0 situation, but RC equal to 1 actually refers to an Otto cycle, and for RC equal to 1 you get the highest efficiency for a given value of compression ratio. In fact, with increase in compression ratio your efficiency decreases. With increase in cutoff ratio the efficiency decreases. Of course, it increases with compression ratio. So, your efficiency it increases with as R increases, but RC has to decrease for this, and RC equal to 1 refers to the Otto cycle. You can see from the expression also the term in this square bracket, here RC is always greater than 1, K is also greater than 1. So, the term in the square bracket will always be greater than 1. If the term is greater than 1, then from here we can easily see for the given value of R, eta thermal for diesel will always be less than eta thermal for Otto. But practically speaking, the diesel cycles or diesel engines always operate with much higher compression ratio than Otto cycle based engines, and therefore, they offer higher compression ratio. So, the advantage of CI engines are superior performance because they work at higher compression ratio, they give higher work output, much better efficiency, and that is why they found application in bigger commercial vehicles. Another commercial reason is the fuel is cheaper. As we are spraying the fuel inside, so we can use heavier fuel and also less refined fuel, whereas in SI engines we need very fine fuel, that is why we have to go for petrol or gasoline, which is a better brand or superior grade of petroleum. But the disadvantages of CI engines are, for the given compression ratio we can see their efficiency is lower, they are heavier and costlier, like as they work in much higher compression ratio. So, the pressure range inside the engines are higher. So, the engine structure has to be much stronger, components like fuel pumps and injectors etc. are also heavier and much costlier compared to spark plug etc. They are pollution prone because of the incomplete combustion, and also because of the higher pressure range, heavier structure, vibration is another problem. That is one of the big issues of not applying CI engines to two wheelers or smaller cars, the vibration related problems etc. Now, we have seen that in SI engines, or sorry, in Otto cycle we consider the the combustion to happen in constant pressure, or sorry, constant volume, whereas in diesel cycle we have seen it to be happening at constant pressure. Practically both of them are not correct. Practically combustion happens partially in constant volume mode and partially in constant pressure mode. So, a somewhat intermediate cycle is defined in the form of the dual combustion cycle, where it is visualized that combustion is partly happening at constant volume and partly at constant pressure. Here this 2x refers to an isochoric heat addition part, whereas this x through 3 refers to an isobaric heat addition part. So, total heat added will be heat added during the process 2 to x plus process x to 3. The heat reaction of course remains the same, that is at constant volume. The same way you can perform the analysis of this one, I am leaving this to you, as we have already done the analysis for Otto cycle and diesel cycle step by step. You will surely be able to do this. I am just giving you the expression for this dual cycle, the expression for efficiency. It will be 1 minus 1 by r to the power k minus 1 to rp into rc to the power k minus 1 by rp minus 1 plus k into rp into rc minus 1. Here this r remains the same, that is volume before compression by volume after compression, V1 by V2, which is greater than 1. RC is the cutoff ratio which corresponds to the isobaric part of heat addition. It refers to volume after constant pressure heat addition by volume before constant pressure heat addition, which is Vx. Rp is called the pressure ratio. It refers to the constant volume heat addition part. It refers to the pressure after constant volume heat addition by pressure before constant volume heat addition, that is Px upon P2. You can see all of them are actually greater than 1, and this expression for dual cycle is a good amalgamation of both Otto and diesel cycle. Like if we put Rp equal to 1 in this, just put Rp equal to 1, see what you are getting. When you are putting Rp equal to 1, it reduces to the diesel cycle. Rp equal to 1 means this point x collapses to point 2. So, your 2 to 3 line will be something like this, which is just what we have in case of diesel cycle. Whereas, if we put Rc equal to 1, it collapses to Otto cycle. Rc equal to 1 means point x and point 3 they collapses on each other. So, the expansion start from this particular point onwards only. So, this will be your expansion stroke in that case. So, you can see from the mathematical expression also. So, this is a good combination of both the cycles. And efficiency point of view, for a given compression ratio, we can always show that thermal efficiency for the Otto cycle is greater than the efficiency for the dual cycle, and that is greater than the efficiency for the diesel cycle. Now, we shall quickly be trying to compare the Otto and diesel cycle in terms of a few parameters. First set of comparison, where we have the same compression ratio, same amount of heat reaction and same state before compression. The Otto cycle diagrams are shown, we have to plot the diesel cycle on top of this. Now, we are talking about same compression ratio and same state before compression. Same state means 0.1 is same compression ratio. So, 0.2 is also same, means 1 to 2 the process remains same. Same amount of heat reaction. Same amount of heat reaction means, as per the TS diagram, the area under this particular curve 4 to 1 has to be the same. So, process 4 to 1 is also same, that is 1 to 2 and 4 to 1 are same, that is 0.1 to 4 they are same between Otto and diesel cycle, but 0.3 can be different. So, we have to see how we can show this, how we can do this. So, Otto cycle is shown here. If we want to retain 0.1, 2 and 4 the same, then how we can have a diesel cycle? Your diesel cycle will be given by this particular line, this 0.3 prime, or if we draw it on the TS plane, from 0.2 we have to draw a constant pressure line. Constant volume line was already shown. If we draw a constant pressure line and see where it cuts this 3 to 4 line, this is your 3 prime, which is the diesel cycle. Now, for this particular set of comparison, which cycle is having higher efficiency? Just check out. We generally like to do it from heat transfer point of view. Eta thermal is equal to 1 minus Q out upon Q in. Now, here Q out is same for both the cycles. Which one is having higher Q in? Which area under the heat addition curve is greater for the Otto cycle, because there the heat addition curve is 2 to 3. Area under 2 to 3 is definitely greater than the area under 2 to 3 prime. So, Q in is greater for this, and from there we can easily say that the Otto cycle efficiency will be greater than the diesel cycle efficiency in terms of this set of comparison. Whereas, if we draw another set of comparison where we again have the same compression ratio, same state before compression, that is 0.1 and 2 or 1 to 2 they are same, but different amount of heat input. Different heat input means process 2 to 3, sorry, same amount of heat input, but heat reaction may be different. So, how we can plot this? Otto cycle is shown, same magnitude of heat input we have to provide. Now, the area under the curve 2 to 3 shows the heat added to the Otto cycle. Same amount of heat we have to add to the diesel cycle as well. So, this is the constant pressure line. If the constant pressure line finishes here, the area under this curve is lesser. So, we have to extend this such that the area under this curve becomes similar to the area under this 2 to 3 curve. So, this becomes your new 3 prime point. So, like this way we have to plot, your 4 prime also gets shifted here. So, your Otto cycle diagram is 1, 2, 3, 4, 1. diesel cycle diagram now becomes 1, 2, 3 prime, 4 prime, 1. If we want to draw the same thing on in case of the PV diagram, then we have to draw it somewhat like this, extend up to some point somewhere here 3 prime, which goes to something like this, and then we have 4 prime somewhere here. So, 1, 2, 3 prime, 4 prime, 1, which corresponds to same compression ratio, same state before compression and same amount of heat input, but different amount of heat rejection. Now, again we compare the efficiencies 1 minus Q out by Q in. Here Q in is same. Which one is having larger Q out? Look at the diagram. Q out refers to area under the heat rejection curve. For the Otto cycle, heat rejection is 1 to 4, or I should say 4 to 1. So, this area is the heat rejection correspond to the Otto cycle. How much is for the diesel cycle? For diesel cycle, your area is this much. So, Q out for diesel is greater than Q out for Otto. So, here again as it is having larger heat rejection, but same amount of heat input. So, thermal efficiency for the Otto cycle is greater than thermal efficiency for the diesel cycle. And one final comparison I would like to do, which is very important from practical point of view, where compression ratios are not same, state before compression is same, which is this 0.1, and the maximum pressure and temperature remains the same. Now, which point in the cycle has the same maximum pressure and temperature? 0.3. This is the one corresponds to maximum pressure and temperature. So, 1 and 3 are same, but other points are different. So, how we can compare them? Again the Otto cycle is shown. To plot the diesel cycle here, 0.1 remains the same. Let us extend this line vertically. This line goes like this, and through 0.3 constant volume line is already there, which leads to 0.2. We backtrack a constant pressure line. So, constant pressure line will be somewhat like this. This leads to your point 2 prime. This is your 2 prime, 3 and 4. Similarly, here actually it is going out of the scale. If you want to plot it here, you have to continue up to this and then somewhat like this. So, this will become your point 2 prime, and 3 remains the same, 4 actually also remains the same. So, which one is having higher amount of heat rejection in this case? Both are having same heat rejection. What heat input? Q in for the diesel and Q in for Otto. Which one is higher? Q in for the diesel is definitely much higher in this particular case, because area under the curve 2 prime 3 is much larger than the area under the curve 2 3. So, efficiency in this case for the diesel will be greater than the efficiency for the Otto cycle for this particular case. These are several other comparisons also we can think of. You can also try to think of a few other comparisons. That takes us to the end of today's lecture, where we have discussed about the Otto, diesel and dual combustion cycles, and also compared the cycles in terms of 3 different criterion. So, in the next lecture I would like to first solve a few numerical problems to show the application of these cycles and how to approach the solution without trying to remember the mathematical formulation, and then we shall be discussing about 2 more cycles, the Stirling and Ericsson cycles. Till then, goodbye.